Hi guys, and welcome to video 13 in the But How Do It Know companion video series. Now the last time we worked on our project board, we left it looking something like this. So we had our bus section here on top, and we completed our RAM connectivity down here. In the next two videos, we're going to be looking at the ALU, which we're going to be building in this section right here. So the ALU is introduced in John's book on page 67, and it is shown in this diagram right here. Now we can see that in this diagram, the big box with a question mark, that is the ALU. And we're going to be looking at what's inside in a bit more detail. So in the next 20 pages or so of the book, John goes on to describe each and every different mathematical or logical function that the ALU implements and how to build each and every one of them. In the end, you end up with a diagram from page 87 that is this one. So the big idea behind the ALU is it's really the brain of our CPU, and it is where the math functions and the logic functions occur. So the way it's built is you have, if you want, 8 sub-circuits that receive inputs and produce outputs. And to control which of the circuit outputs the answer, you have for each of them an enabler, and there is at the bottom a 3x8 decoder in which you will send a code, an operation code, that will indicate to the unit for which operation you're interested in receiving the result. So we're not going to go into describing in detail each of these different functions because we'll see that most of them are really quite obvious. So for example, if we look at the XOR, the OR, the AND, or the NOT functions, they are really just the simple logic gate operations that we have seen before that operate on 2 or 1 bits of input, but now they are applied to 2 or 1 bytes. So it's quite easy to imagine that you can implement the XORer, the ORer, the ANDer, or the NOTer using the specific chips that we've looked at in the previous video. For example, the NOTer could be made using 7404 chips, and 08, 32, or 68 chips for the other AND or XOR functions. So already there we can see how we can build half of the functions of the ALU in a pretty much straightforward fashion. Now if we move down, we have 2 more functions, which are shift left and shift right, and these don't really have any logic gates to them at all, so they are just connecting basically the input and the output in a specific fashion to shift the bits right or left. So that leaves us with really 2 sub-circuits here that are a bit more complicated and of interest, which are the adder and the comparator. So we're going to be looking at those in a bit more detail right now. So first we're going to be looking at the adder function. So there are 2 kinds of adders that are discussed in the book on page 79. The first one is the half adder, and the second one is the full adder. Let's start with the half adder. So if we look at the diagram here, we can see that the goal of the circuit is to perform addition of 2 values, A and B. So the main part of it goes into the XOR gate, which gives us our sum. And if you think about the truth table of the XOR gate, and the possible values for A and B, it really makes a lot of sense. If A and B are 0, you will get a sum of 0. If A or B are 1, you will get a sum of 1. And if A and B are both 1, then you will get a sum of 0, and you will have a carry to bring over to the next column of numbers. So the carry is handled by the AND gate at the bottom, which will return true. If both A and B are true, then we will have a carry. If we move over to the full adder, at its core, it's really the same as the half adder. You have that first XOR gate there on the left, and the bottom AND gate are the same ones that you have in the half adder. Now, where it gets a bit different is that the full adder can support a carry in value, which means that it can do basically the addition of 3 values, A, B, and the carry. So the carry comes in the middle of the diagram here, and its value is XORed with the sum of A and B to give us our final sum. And it is also sent into another AND gate where it will be ANDed with the sum of A and B to determine if a final carry is required. So a final carry can be required if either A and B are both 1, or the sum of A and B is 1, and we had a carry in to begin with. So those two AND gates are ORed together in the final carry out OR gate that is at the bottom of the diagram. Okay, so I have built a 2-bit adder here that we're going to be using to look at more detail at the adder circuits. So the idea is to add these two 2-bit numbers here, this one here and this one here, using a half adder and a full adder. So the least significant bits of these numbers will be added together using the half adder, and the most significant bits using the full adder on top. The carry out from the half adder is sent as the carry in for the full adder. So let's start with the half adder. Its input are the yellow and green wires here. So those two signals are XORed together using an XOR gate here from this SN74HC86 chip. So the result of this XOR follows this orange wire here and goes straight to this LED, which is our leftmost sum value. The same signal are ANDed together here using an AND gate from this SN74HC08 chip to produce the carryout of the half adder, which will be leaving through these two blue wires here. Now if we look at the full adder, it's going to be adding the red signal here and the purple signal here. So they are going to be going into the first XOR gate here. This is going to give us our first sum, which is going to be XORed with the carryout of the half adder, giving us our second sum value here, which is going to go straight to our LED. These signals are also going to be sent to an AND gate here together. There's going to be another AND gate here that will be getting our sum and the carryout of the half adder, and both the results of these two AND gates here, this orange wire here and this purple wire here, or blue, will be ORed together, giving us the final carry out value. So let's take a look and see how it works. So initially, when all the values are 0, we have no LEDs that light up. let's try turning 1 on. So this in effect is adding 0 to 1, and it gives us a sum of 1. Adding 0 to 2 will give a sum of 2. 0 to 3 gives us a sum of 3. So far so good. Now if we use 1 as our first value, so 1 plus 0, 1. 1 plus 1 is 2. 1 plus 2 is 3. And 1 plus 3 gives us basically 4. So a sum of 0 plus our carry out here. Let's do the same thing with first value of 2. So 2, 3. 2 plus 2 equals 4. 2 plus 3 equals 5. And finally, we start with 3, which gives us 3. 3 plus 1 is 4, so our carry out is on here. 3 plus 2 equals 5. And finally, 3 plus 3 equals 6. So 2 and carry out. So in order to construct an adder that can add 8 bytes together, you have to string together 8 full adders, and it will allow you to add your full 2 bytes and have your carry out if required. Okay, now we're going to be looking at the comparator circuit using this diagram from the book on page 83. So the comparator circuit has 2 inputs, bit A and bit B, and it has 2 outputs. Both outputs represent attributes of the relationship between A and B. So the first output will tell us if A and B are equal. The second output will tell us if A is larger than B. So how do we test for equality of 2 bits? We start by using an exclusive OR gate, and that will tell us if the bits are different, right? Because in an XOR truth table, if A and B are both 0, you get 0, and if A and B are both 1, you get 0. So you get 0 when they're equal, you get 1 when they're different. So if we send the output of this XOR gate to a NOT gate, we will get a signal telling us if the 2 bits are equal. So the way the comparator works is similarly to the adder, is they will be all chained together. So if you want to compare 2 bytes, you will chain 8 comparator circuits together to get your answer. But contrarily to the adder circuits, which are chained starting with the least significant bit, for the comparator, you start with the most significant bit. So to check if 2 bits are equal, all the bits that you have seen so far have to be equal, and those 2 under inspection right now have to be equal. So that's what that AND gate number 3 does. Then let's move on to the next output, A larger. So for A to be larger, what does it mean for A to be larger? It means one of 2 things. All the bits that we have seen so far are equal, and A is 1 and B is 0. So that's what the gate number 4 is doing. So that's a 3-input AND gate. So it says if everything I've seen so far is equal, and A is 1 and B is 0, then A is larger than 0. Than B, excuse me. But one other way for A to be larger is that it could be that whatever we've seen so far is already larger. So since we're starting with the most significant bit, if the first leftmost bit, say, of A is 1 and B is 0, no matter what we see later on, A is always going to be larger. So either A has been larger before, which is the rightmost branch of this OR gate number 5, or everything was equal and A is larger for this current bit. So those two outputs, equal and A larger, are called flags, and they are part of 4 flags that are output by the ALU. And these flags are going to be very useful later on when we look at jump instructions and of different ways to alter the execution of a program that's going to be running on our CPU. So let's take a look now at a 2-bit comparator that I've built and see how it works. Okay, so here's my 2-bit comparator circuit. So it's going to compare this 2-bit value here, A, with this 2-bit value here, B. And it's going to produce these two outputs, A larger here and equals. I'm not going to go through all the details of the circuit right here. I'm going to leave that as an exercise for you guys. I'm just going to point out to you what kind of gates I'm using here because it might not be obvious and you may not be able to read. So this is an SN74HC86 gate, so XOR SN74HC08 and SN74HC04 not. I didn't have enough space in here to use an OR chip, and since I needed only one OR gate, I created one using these diodes here. So I'm not going to explain how to do that, but I'll put a link to a video that shows it very well in the description box below. So like I said before, I'll leave it as an exercise for you guys to figure it out how the comparator works here. I've taken a couple of shortcuts also because the way you kickstart your chain of comparators is by feeding in a 1 signal for the equal so far and a 0 signal for the A larger. But if you have constant values coming into an AND or an OR gate, in some cases you can just get rid of it, and that's what I did. So let's see how it works. Okay, so both our values are 0 here, so it's telling us that A is not larger, and that they are equals. So let's turn this bit here to 1. So we're comparing 0 and 1, so they are not equal, and A is not larger. If we compare 0 and 2 or and 3, we have the same results. Now let's put a 1 value in our A number here. So now it's telling us that A, which is 1, is larger than B, which is 0, and they are not equal, which is correct. Now I put both to 1, so it says that they're equal. I'll keep incrementing B here. And 1 and 2, so A is not larger and they are not equal. 1 and 3, we have the same result. Now let's start with A equals 2. So A is larger, A is going to remain larger until we get to a bigger number, but first we have to go through 2, so 2, 2 equal, and 2 and 3. Now A is no longer larger. And finally, A equals 3, so we have A larger, and now A remains larger until it is equal, and we have 3 in both bits. So that's it for the comparator circuit. There are 2 more circuits that we will be requiring to complete the build of our ALU. One is the 0 circuit, and we see it in the book on page 84. And the other one is the bus 1 bit 1 circuit, which is shown on page 90 of the book. I'm not going to go through those. They are fairly simple to understand, but you need to be aware of them because we're going to need them in our final implementation. Now, I thought I would finish off this video by showing to you guys a couple of pictures from an actual fully blown SN74HC chip implementation of the entire ALU unit that I built a while back. Okay, so here's a picture of the entire ALU that I have built. It's made up of many breadboards, each of them implementing one or two of the different ALU functions. So I split it up into 4 pictures so that we can zoom in a little bit more. So this is the top part right here. So on the very top we have the bus, just like in our own project. And below the bus on the left we have the accumulator register, which is going to be where the ALU sends and stores the result of its last computation if we need to remember it. Below the accumulator is the 0 circuit, which will provide us with the 0 flag telling us if the result of the ALU computation is 0 or not. Then if we move on to the right, on top we have the TMP register, which is used to store one of the 2 values that serve as input to the ALU. So the ALU will take TMP as one input and whatever's on the bus as the other one. Below the TMP is actually the bus 1 circuit. There is no label on this one, but it is used to send a quick 1 value to the ALU to perform an increment operation. If we move on to the second part here, we have 3 of the basic ALU functions, so ANDR, OR, and exclusive OR. So what you see on the left is actually the enabler parts for these circuits. So each enabler is sending into that brown bus there that you see on the left, and that goes into the accumulator. So on the right, the 2 chips there are used to AND the ALU inputs together. So they use SN74HC08 chips. And below that we have OR, so SN74HC32 chips. And finally, SN74HC86 chips for the exclusive OR. In the next part here, we have the adder. So again, on the left, we have the enabler. And on the right, we have the actual chips that do the adding. And these are SN74HC283 chips. So they are chips that have the built-in adder logic inside them. Moving down, we have the nodder on the left, which is implemented using SN74HC04 chips like we've seen before. And on the right is the comparer. There is a dedicated chip to compare 2 bytes. It's an SN74HC682 chip. So that's what I used here to build my comparer. And finally at the bottom, so on the left side we have our left shifter and our right shifter. So those they have their own enablers, but they do not have any chips. It's just wiring that's involved. Right next to them you see some LEDs there. The yellow LEDs are actually the ones that are showing the operation that has been asked of the ALU. So that those 3 inputs, and below is our flags. So our carry out flag, a larger flag, equals flag, and 0 flags. The white LED that's there is to indicate if there is a carry in input or not. Then moving to the right, we have a bit of OR circuitry here that is used to handle the flags. And at the bottom, you have a 3x8 decoder, which is an SN74HC 138 chip. So that builds a complete ALU out of SN74HC chips. So in the next video, we're going to be hooking up our ALU to our project board. So since it's going to be simulated, in this case, again, we're going to add a new Arduino for that, and we're going to be putting in place all the wiring. See you soon.